Hello students, welcome to this lecture where we will continue on the activity factor, and using that particular activity factors we will try to evaluate the overall or the average power or the the dynamic power, the switching power, as well as the switching energy and then the dynamic energy. Right, so the last time what we had seen is an output with ABCD as a logical expression. So we had two input NAND gates, two input NAND gates, and then followed both of them were connected in the next stage where in the NOR gates, and then where we got the output as ABCD. So, and we call this as a multi-stage architecture because it is of two-stage circuit, and we try to estimate the alphas between each of these output nodes, the alpha here, and then the alpha at the final output node. So in this particular architecture, we call it as a chain architecture. The reason is there are multiple stages here, and the final output is the same, but it forms in the form of it is being evaluated in the form of a chain architecture, right? So if I consider ABCD here, using a two input NAND gate, I'll get AB bar if I supply the input of A and B. The output of this particular two input NAND gate can be supplied to the inverter, and then here the output will be AB. Supplied to another two input NAND gate with a C input, I'll get ABC bar. Inverted output will give me ABC. Supplied that to the two input NAND gate with the D as another input, we will get ABCD bar, and then with the inverter we will get ABCD. So this is my overall logical expression, and if I consider this particular method and then this particular method, the overall logical expression remains the same, right? But one we call it as a multi-stage, here we call it as a chain architecture, and it is, you can consider this because we evaluate AB first and then ABC first, and then we will evaluate the ABCD. In that sense also it can be considered as a chain architecture. So one thing to note here is I have a lot of output nodes here. Whereas in this multi-stage architecture, I had only 3 output nodes. So we need to extract the capacitance at each of these nodes, and then multiply or estimate the activity factor at each of these output nodes, and then multiply that activity factor with that of the capacitance, and then do the summation, and then multiplied by VDD square will give me the switching energy or the dynamic energy. In this particular case, I actually have a lot of output nodes. There is an X output node, there is a Y output node, there is a W, there is a U output node, V output node, and Z output node. So in fact, the number of output nodes where I need to estimate the alphas and then where I need to estimate the capacitances turns out to be 6 in this particular chain architecture. Whereas in the multi-stage, it turns out to be the number of output nodes is nothing but 3. So let's try to evaluate the activity factor and then try to estimate the overall energy term or the power term. So the probability at the point X, the X being 1, is nothing but it's an output of a 2 input NAND gate, so it will be 1 minus PA PB. Considering the same input probabilities of 0.5 across all the inputs, so we will get 1 minus PA PB, which is nothing but 0.75. So alpha X turns out to be 0.1875. Right, and it is very similar to that what we had got for the multi-stage architecture at the node X, right? At the node Y, I'll have the inverted output of the X input, so it is nothing but 1 minus Px, so 0.25. The activity factor will be nothing but Py and then complement of Py, so it remains the same as that of the Px or whatever the activity factor at the X node. So even the Y node will give me an activity factor of 0.1875. And remember that the Y node output is an output of the inverter. Right, in the multi-stage architecture, we had got the output here as 0.875, the activity factor at that output node here, and then output node here was nothing but 0.1875. PW, which is nothing but the probability at the output of the second 2 input NAND gate, is nothing but the Py here and then the Pc here, right? Depends on it's a function of Py and Pc here. So 1 minus Py Pc, and Py is now 0.25, Pc is 0.5, so I will get the Pw as 0.875, alpha W turns out to be 0.109375, right? It is a kind of a different number to that of the 0.1875. and PU, which is nothing but the inverted output of W. So I'll get 1 or rather 1 minus 0.875, which will be 0.125, and alpha U will be very similar to that of 0.109375. Right, so if I do calculate alpha U from this 0.125 multiplied by 1 minus 1.125 will give me 0.109375. PV is nothing but it's coming from the third 2-input NAND gate, so I will have to, it's nothing but a function of PU and PD. So 1 minus PU and PD, so that will be 0.9375, and alpha V will be nothing but 0.05859. So this is something we had got previously also. So we had got this particular value, and we had got this particular value of the activity factors. And then finally this PZ value, which is nothing but the inverted output of the V signal, which is nothing but 0.0625, and then the activity factor of 0.05859. Right, so we achieved at the output node of Z, we actually achieved the same activity factor as that of the earlier case. So if you remember, I had here the activity factor of 0.1875, here 0.1875, and here it was nothing but 0.05859. Right, which is what we had achieved here also, 0.05859. So the overall activity factor achieved by this particular chain architecture remains the same as that of the multi-stage architecture. And the reason is very simple, because this activity factor are evaluated from the logical functionalities of the gates. So the logical functionalities of both the architectures being the same, we should be able to evaluate the activity factors also to be the same. Right, so we will get the same activity factor. But the difference here is, if I need to find out, the overall power or the overall energy here, the capacitance is here, the capacitance is here, the capacitance is here, and here, right, needs to be multiplied with the respective activity factors, and then of course multiplied with that of the F clock and then VDD square. And this is what the total power turns out to be. So I have an F clock and VDD square, and then multiplied by that of the summation of the alpha i's and ci's, which is nothing but so alpha for that particular node multiplied by the capacitance at that particular node. Right, and if I notice this, my alpha x is 0.1875, alpha y is 0.1875, alpha z is 0.05859. Right, but we have an extra alpha w, alpha u, alpha v. Right, so let me say that alpha w was 0.109, alpha u was I think 0.109, alpha v was nothing but alpha z, which is 0.05859. Right, and even if I consider the widths of all this 1 2 3 4 5 6 gates, right, I will specify some kind of a width so that the overall capacitance of Cx plus Cy plus C sub W plus Cu plus Cv plus Cv, okay, Cx, Cy, Cw, Cu, Cv and Cz, right? If I equate it to my multi-stage architecture Cx plus Cy plus Cz, so this is my multi-stage design. And let's say this is the architecture design, the chain architecture design, right? So if I do that, the chain architecture and then the multi-stage design, even if I say that all the parasitic capacitances or the capacitances seen at the internodes of all this, of both the circuits, if it is same, right, even then my alpha values, there is an extra alpha v, alpha u and alpha w, which is going to give an extra power. Right, so what I've done is, in this particular case, alpha v is 0.1875 and alpha z is also 0.1875. So we can choose one of them. So if I choose alpha v with that of alpha x and alpha y being that there in the previous case, but still I will have alpha z, alpha w and alpha u multiplied by some capacitances, and then the overall the power is going to increase. Right, so having more nodes or having more stages, especially in the chain architecture, although it is going to give me an the same logical expression, right, but still I might have an extra power. Right, I'll be able to this particular chain architecture is going to dissipate or the VDD rail has to deliver more power or more energy, right, for the chain architecture. There is one more aspect which we tend to ignore while calculating the energy, the switching energy term or the switching power term. And let's try to see that in this particular timing analysis, right? So let's go back to that multi-stage architecture. Again, I'm going to draw that multi-stage architecture. So I have two inputs, two input NAND gate followed by the NOR gate. So I will have A, B, C. And C and D, and then here is my X, here is my Y, and then this is Z, right? So this is my OR gate, and then these two are two input NAND gates, right? Let's take an input here. The input is ABCD, which changes from 1101 to 0111, right? So it's basically an AND gate. So the output here for ABCD, at the output at this Z node, the final output basically should be 0 here and should remain to 0, right? So in a multi-stage architecture, let's try to draw this particular transitions, right? So the input starts from 1. So if I look into this particular expression of ABCD, changing from 1101 to 011, so it is nothing but A is actually changing from 1 to 0, and B remains the same, D remains the same, C is changing from 0 to 1. That's about it. So B and D remains the same, remains 1 throughout. So my timing diagram says that B remains 1 throughout, D remains 1 throughout, A is changing from 1 to 0, and let's say that C is changing from 0 to 1 at the same time. So when the transition of A happens from 1 to 0, at the same time the C also does the transition. So let's take a very ideal case and let's try to identify what happens, right? Let's try to accommodate this particular input transitions into our multi-stage architecture as well as the chain architecture, and inside try to evaluate the final output expression. So if I have this ABCD where B and D are doing the transitions, or rather B and D remains 1 and A and C are doing the transitions, the output of X here, the output of X will be nothing but, if B is set to 1, the output of X is nothing but an inverted output of A. So X, will be, so A and B NAND gate. So 1 and 1, so it will be 0 throughout till A does the transition from 1 to 0. So the moment it goes to 0, A goes to 0, I'll get an X going high, and that's what it is. So this is nothing but, I'll say it, propagation delay rising, right? So with respect to the timing parameters, I'll say that when the A goes down, that is when the X is going to go high. So there will be some kind of a delay. Right, so there will be a gate delay for this particular NAND gate, and that will be characterized by the propagation delay rising. Let's consider the Y output. The Y output is nothing but C and D, where D is set to 1, right? D is set to 1 throughout. So I have a D which is continuously 1. C is actually doing the change from 0 to 1. So again, Y will be nothing but an inverted output of C. So whenever the C changes, so there will be a change in the Y. When the C was initially 0, I'll get a Y to be high, and then when the C does the change, Y is going to, C does the change, rising change, the Y output will be low. And because C and A are doing the changes at the same time, I will also get, and if let's say that this gate and then this gate are actually having the same kind of a width or sized in a very similar manner, then I'll get the same delays. So for the Y output, I'll get the falling delay with respect to the C. Whenever the C starts rising, I'll get the Y output to be falling, right? So I'll get this as nothing but the propagation delay of falling. Finally, the Z, which is nothing but the NOR of the output X, of the input X and Y, right? So the output Z, so if I consider X and Y, so X and Y were 0 and 1. Right, so the output Z will be nothing but 0 here, and here also it will be 1 and 0. It does the transition at the same time, so 1 and 0, I will get the output of 0. Right, so assuming both the gates have the same delay and all the inputs are arriving at the same time, so this is what we will get the Z output. Right, so if I consider the X output here, right, the X is doing the transition here, and then Y is doing the transition here, and somewhere else it will do the higher transition again. So this particular alpha activity factor of X accommodated with that of the capacitance at Cx, so that we will get the energy term C VDD square, and alpha Y Cy C VDD square. So this particular what do you say, a legitimate transitions, especially in this case, and then in this particular case, which is arrived because of the logical expression of this particular two input NAND gates. Right, so both these expressions, one going high and one going low, have been attained or have been achieved by this logical functionality of the two input NAND gates. So whatever is this transition, this is anyways been accommodated in our energy term, because alpha Y accommodates the logical functionalities, right? So it actually depends on alpha X depends on the probability of the inputs being 1 and 0. All right. So moving ahead, let's take the chain architecture. So we have the chain architecture, that means A and B and C and D. A and B will create X, and then X inverted will be Y. C and Y will give me W, W's inverter will be U, U and D will give me V, and then the inverted output of V will be Z. Right. And let's say I will take the same example, the input doing the transitions, in this case being ABCD, starting from 110 to 1101 to 011. Again, the same thing, A is changing from 1 to 0, and C is changing from 0 to 1, and B and D are retaining at the logic level high. So that's what I've done. B and D are retained at logic level high. A is doing the transition. C is also doing the transition. And just to benchmark against the multi-stage architecture, what we have done is we have taken the transition at the same time, right? A and C doing the transitions at the same time. So let's try to find out what is X. So X will be nothing but the inverted output. It's in a two input NAND gate where one of the input is high. So it will be nothing but the inverted output of A, right, with some particular delay. So whenever A is high, I'll get X to be 0, and whenever A goes low, I'll get X to be high, and then this particular delay is called as propagation delay rising off the two input NAND gate, right, the first two input NAND gate. Y is nothing but the inverted output of X. So Y will start with high, and then whenever X goes high, Y will go low. So I'll get based on the propagation delay falling of the inverter, I will get this particular signal of Y. W is nothing but the two input NAND gate of Y and C, right? So it is nothing but the two input NAND gate of Y and C, right? So this is kind of a little bit interesting here. So that's what the W is. So when C is low and Y is high, the output should be high, and that's what it does. The moment both of them in this particular case, because of the delay in Y, both in this particular region, when Y is high and the C is also high here, so high and high, I'll get the output to be low, and that is what based on this particular CB going high, I'll get this particular delay. Due to this particular delay or the transition state, I'll get the W output going 0. So this will be propagation delay falling. And then C stays at high, but Y goes low here. So during this particular transitions, I'll get 0 and 0 at the inputs of the two input NAND gate. So my output will be high. So that means that W has to go high again, right? So the W goes high again. What it implies is W going high, I will get unnecessary transition here, right? So this circle which I have drawn here, right, it's an unnecessary glitch or an unnecessary transitions, one going low and one going high, just because of this particular propagation delay, right, in the circuit, right? So the TPDF, right, and then the TPDR. So what it means is the Y, which is kind of delayed due to the X, X kind of getting delayed by the gate delays. But the Y, the inverted output will have some kind of a delays, and then the delay in the Y is going to give me this kind of a small glitch of going low and then coming back high, right? So this particular transition is a glitch, and what happens is the output of W is then passed to an inverter. So the inverter also shows or throws a glitch again here, which is an inverted glitch of this. So I will have when W is high, the U will be 0. And then we will have this going low and high In the U, it will go high and then come back low. Right, so there will be a glitch here which is kind of propagated from the W signal, and then this particular one will finally go to the 2 input NAND gates, the W output, or rather the the U output will go to the the U output will go to the 2 input NAND gates, where the other input is D, but the D is a constant 1. So the output of the 2 input NAND gate, the fourth, the fourth means X being the 1, and then W being the second one, and then of course the third two input NAND gates in the chain architecture, we will get, because D is 1, I will have an inverted output of U. So I will have a U, whatever is U, the inverted output of U, so it will be high, and then when it goes high and low, it will go low and high. So again, this particular glitch is kind of propagated to V, starting from W to E to V via the U. And lastly, the Z output, which is nothing but the inverted output of V. So I will have the inverted output. So this particular glitch is kind of propagated from W till the Z output, till the final output. So if I consider the logical transitions here, if I consider the output Z transitions, so what I really want is the Z to be staying low throughout. But here I have this particular transition. So what the transition indicates is the capacitance at the Z output is going to get charged, right? Capacitance at the V output is going to get charged, right? Capacitance at the U output is going to get charged. The capacitance at W output is going to get charged, right? So the glitches add an additional transitions which is not accommodated or not incorporated in our overall estimation of the activity factor. Right, remember that this particular glitches are coming not because of the logical functionalities of the gates, but because of the delays. Right, so if we don't actually accommodate the delays here, I will actually not get this particular glitches at all. So if I consider the delays are 0, so I'll get the transitions whenever the C is doing the transition. That is when the X is going to do the transition. That is when the Y is going to do the transition. That is when the W is going to do the transitions, and so on. So in that case, I will not have this glitch at all. And what happens is, because of this delays, I will get an unnecessarily transition at the output, and then it has to go back to 0. So an unnecessary transition of at the output node from 0 to 1 will cause an additional energy or the power to be delivered by the VDD relay. Right. So the chain architecture delivers an additional energy of C VDD square, right? CZ VDD square. So the capacitance at the Z node multiplied by VDD square, CV VDD square, and then CU VDD square and CW VDD square, right? Which is not accommodated in our alpha calculations for the energy term, right? So these are additional ones, right? So that is something one has to take care, and that's why having more number of output nodes, or especially in the chain architecture, is not a feasible it's not an energy aware design. So if I really want to have the power benefits or the energy savings, then actually we should go towards the multi-stage architecture design, right? So the switching probability assumes the 0 TPD, because it always, it has been defined by the logical functionalities of the gates, and it doesn't accommodate the delays at all. But in circuits when the inputs do not arrive simultaneously, right, the output transitions will be many times. We'll see more frequency of the output transitions, and thereby increasing the power dissipation or the energy delivered by the VDD.